ACE 111 Lecture 8, Set 3. In this example, we are going to go through the details of the design of a data path and a control path. It is, always, from a high level, could work like a mystery how the digital systems work. But, in reality, it's nothing else but a finite state machine. And now we're going to go about designing a very simple finite state machine that does these ALU operations to get your hands on into what is really happening inside a processor. Now, the data path where, we do the operations on the data are combinational circuits. And then there are registers on here which store the intermediate values. The control section is going to say what is going to get combined with what, and which register you're going to load the data and which register the results will go. And this is going to generate the control signals. It select the right operation to perform, enable registers that are going to be selected, and then the status signal from data path is telling us if the units that you're trying to use are busy or they're available for us to do this these kind of operations. Of course, you could make it way more complex than it is, but in this example, we're going to talk about the design of a very simple data path control path. So imagine that we have a complex multiplier where we have two complex numbers. The first one is A real plus J A imaginary, and the second one is B real plus J B imaginary. And we know what happens when we multiply these two numbers is that we get the real part becomes ARBR minus AIBI, and then the imaginary part becomes J and AIBR BIAR. So, this is just basically simple middle school math that we're going to talk about. But, we want to have this in the fixed point format, and we are subject to tight area constraints. And what that means is that we are going to use the multipliers, adder, and subtractors to do this. But of course, if you just go straight forward with these operations, have the controller schedule them, and with one multiplier and one adder or subtractor, which I could convert with, just basically the 2's complement method, I could do these tasks with, under the area constraint. And now let's see how that actually works in practice. Imagine that I have this real part and imaginary part of the A coming to a multiplexer, and real part and imaginary part of B coming to a multiplexer. And I have a selector which selects which of these two bits I'm going to select. And, if I'm selecting, for example, ARBR, that means that, my B select is 0 in both cases. And then what I'm going to do is I'm going to multiply them. And I'm going to put the result of this multiplication in these registers according to the control signal. If I enable this register, I'm going to have the results here stored here. And if I enable this other one, I'm going to store the results here. And then I could do either addition or subtraction. And if I'm doing subtraction, there is a control signal for the subtraction. And then once I get the results, then, if it's the result, let's just go back. If it's the results from this first one, now I'm going to put it, say, in one of the final registers here. Basically, the real part goes here, the imaginary part goes here, and then I'm going to have the final results for the real and imaginary computation and have this output to the system. Of course, these registers are all orchestrated by the clock, and as you could see here, the selector signals are pretty straightforward. I'm either doing, the operation that are suggested and, doing this multiplication and storing the result here, or I'm doing this operation with the signal selected here and storing the results here. And if I have these two results, I could go ahead and do the next operation because, I have computed this one, and then I'm going to go and do this whole parentheses. And then I'm going to go and do the same with the second parentheses, and then I'm done. Now, the question is, the big question is, like, I understand this flow, it may take you a little bit to try to go through this example and digest it, but it's not that difficult. It's just like, you have to think about all the steps that goes on with having only one multiplier and, one adder subtractor. So this is the one multiplier and one adder subtractor, which is doing this operation. But once you understand this, the selection signals are pretty straightforward, and I could definitely go ahead and write the controller. So the controller tells me if I'm in the first cycle, I need the real part and of A and B, and I'm going to, so A select is going to be 1, it's going to be 0, B select is going to be 0, and then I'm going to this multiplication happens, and then I'm going to put the results in the upper register, and so this one is enabled and this one is disabled. So this is 1, this is 0. The subtractor doesn't really matter, so it's a don't care because I'm not really at that stage yet. And then these two are basically like kind of not mattering. Before I go through this complex multiplier, I could actually go ahead and talk about the module multiplier with respect to the input and output signals, because I have all these inputs here and I have these outputs here, right? And I have the clock and reset signal. So I could design that interface that I have standard for these. So I have the real and imaginary part for the partial products that are stored in these multipliers. And then I have the inputs that are a real and imaginary part of AI/BI. And as you see here, the length of this is half of the length of this because it's the multiply of these two. And then I have, of course, this clock signal and the input ready, which tells me if the input is ready for doing these operations, because the data path may not be active all the time. And then these wires are actually signed wires, because it's going to make a difference if I have negative or positive numbers. And then we are going to have these in the same order that you see here. We have these wires here, and then we have these registers here, which we are going to determine in this example. And if you could you could basically just write it like this with just a program without even going to a state transition diagram. So we say, if you're in the beginning and if you have the A real, B real, and this B select and A select are 0, then we are going to do this operation. And then we are going to put this result in the PP1, so the temporary register 1. And then if we have the second clock, we're going to do the second partial product, and then depending on the on the sign, what we're going to do is we are going to either add these two partial products or subtract these two partial products, depending on if we are on the real part of computation or imaginary part of the computation. And then now we are done with the first part of this data path, and the second part is going to be just saving the partial product in these two registers and outputting it when necessary. The multiplier control sequence, as you see here, the first step we are doing a real part of A, real part of B, and put it in the PP1 register. In the second step, we're going to do the imaginary times imaginary of A and B and put it in the second register. In the third step, we are going to do this subtraction and put it in the R register, then kind of so on and so forth. And as you could see, this takes 6 clock cycle. Now, the question is, can we do better? Is there a way we could do it in less clock cycles? And the answer is yes, because, you know, as you see here, we have one multiplier and one adder. And what that means is that, you know, here the adder cannot work because it's waiting for the results of these two first registers to complete. But at this stage, you know, we have the real part times the imaginary part of A and B. So basically what happens is that, you know, once we are done and we are here, we could still use this first part and do the calculation here in parallel with the calculation that we have here. And that's how we can save 1 clock cycle here. So we have, you know, combining these two, we have 5 clock cycles. And again, we could easily translate this to a series of zeros and ones, which says in which step what is asserted based on this diagram. So we have the real part of A, which means select the 0, the real part of B, which means the select the 0 on B, and then this register is selected, and everything else is, you know, either don't care or not selected. And, you know, we go through this step by step and just fill in the zeros and ones in this transition function. And, you know, as you could see here, we could have one state per step. And, you know, we could have a separate one for the idle step, basically one which waits for the input ready. Before the input comes, it's not going to go to any states, but once the input is ready, is asserted, it's going to proceed on the, because we know once the input is ready and we want to do this computation, this is just going to go in very standard steps. It's not like the diamond nickel that we are waiting for something to be input. This is a pretty straightforward control path sequence that we take when we know that we are doing a multiplication. Now, the output function, you could design it however you want. You could design it as a milli machine. You could design it as a Moore machine. And here I'm just writing the Verilog interpretation of this. As you could see here, you know, if you have that table which says, you know, in which step, in which, you know, what are the states that we determine, then you could just write this case as the current state, and then, you know, if this input is not ready, then of course, you know, if not input ready, you're going to stay in the same state, but if the input is ready, you're going to go progress throughout the state. And the reset state here is determined to be the state step 1. As you see, this is actually not a system Verilog code, this is a Verilog code. It's good to see this practice in various formats. Always at positive edge of the clock is determining the flip-flop or the combi or the sequential part, and always at star is the next state logic, which is determining the combinational part of the design. Now, you know, this is the, again, this is kind of the output logic. In this particular example, like, you know, the output logic is determined like step by step here based on which step we are and in the current state, and that's how we interpret that module to a Verilog form. Now, you know, one thing I can tell you is that I can talk here all day, give you many different examples and show you the code, but like any other coding exercise, you would not be able to write things correctly unless you get your hands dirty. So start by doing, these designs, try to compile them, try to debug them, try to see what is it that, is the combinational part, what is it that the sequential part. It's a very practical field that needs your experience, and unless you practice on real examples, you would never gain the skills that help you design a real finite state machine. So I really encourage you, start from the simplest example, which I believe was that finite state machine for the parking lot. Try to write it, try to compile it. I may have some typos here and there, but that doesn't really matter. You should be able to understand and write your own code and try to understand which part is combinational, which part is sequential. Unless you go through that understanding, doing the homeworks and the project for this course would become drag, and I don't think it's any difficult exercise. It's just like anything else, you have to practice and make it perfect. All right, so we will be talking about how, once you write these finite state machines, how you write the test benches to test if they're doing the correct thing, which is another important step in designing them.